All right, so we are going to talk about agent differentiation, its application in machine learning and finance, how it all connects together, and how it resolves otherwise difficult problems in these two fields. All the slides and all the workshop material is available in my GitHub repo. You may want to take a note of the address. And let's start with the introduction. So what is agent differentiation? That's the subject that we are going to cover here. An agent AD is an algorithm to compute the many differentials of a scalar function quickly and accurately. By scalar function, I mean a function that takes potentially a large number of inputs, but which result is one real scalar number, and this is important. AAD will otherwise not work so efficiently when we have multiple outputs. So by quickly, I mean in constant time. Means that AD computes all the differentials of a given function in a time similar to one evaluation of this function. And accurately because this is an analytic differentiation, so it's accurate to machine precision. So the application in finance and machine learning and any other field is whenever we need to compute many derivatives of one result. And we are going to see many examples of that, of course. But this is everything AD does. AD is about speed in the computation of differentials. It doesn't do anything else. And AD has been hyped a lot in the recent years. And while I have been teaching and presenting this material, I have seen very unrealistic expectations towards AD. Some people thought that the AD could help them risk manage their derivatives books better. AD is not going to do that for you. AD will just calculate the derivatives faster. Your risk management strategy will be as good as your model. AD cannot help with that. I have had some questions that reveal an expectation that AD could perhaps magically compute differentials of non-differentiable functions like discontinuous payoffs, digitals, or barriers. We are going to see examples of that. Of course, AD cannot do that. You can't differentiate a non-differentiable function. That's why it's called non-differentiable. And AD will not help you. The only thing AD will do for you is compute many derivatives very quickly. So maybe it sounds disappointing, maybe it sounds niche, but neither machine learning nor financial risk could not work without it, because it's only about speed, and yet it makes a massive difference. Deep neural networks could not learn their parameters in reasonable time if we were not able to calculate differentials of cost functions to their many parameters in reasonable time. We could not compute financial risks are of derivatives books and capital calculations and XVA in reasonable time with conventional differentiation either. Have an article on QuantMinds about this subject. The article is non-technical. It's a journalistic, qualitative introduction to AD, what it can do and what it can't do, if you are interested to find out more. So speaking of application, one major family of applications of AD is model fitting. So in the general sense, we consider a model something that makes a prediction, a scalar prediction y hat, from a set of inputs x. So x is a vector, and given a set of parameters theta. So a model will just be a function of a vector x, my input, and a set of parameters theta. And this parametric function, I will use it to make predictions for a target real number. And I will call y the prediction given by my model. Now, before a model can be used, it must learn its parameters. It must specify this vector theta. And it usually does it by iteratively minimizing a cost function. So we will give our set a training set of m, of a number m of labeled examples, for which we know not only the inputs, but also the true value of y. And we are going to measure the errors that my model makes in predicting these y's. And we are going to set the parameters of the model so as to minimize the prediction errors, which are usually measured, it doesn't have to be, but which are usually measured as a sum of squared prediction errors. In nearly all contexts, other than the simplest ones, like linear regression, say, and with a remarkable exception of, say, Duper's model in finance, where the parameters, the local volatilities, are given explicitly as a function of observed market prices. In most of the cases, we can't have a formula, we can't explicitly express the parameters that minimize the prediction errors, and we must follow an iterative minimization algorithm. So what it means is that we will take a wild guess, an initial guess for what the parameters could be, and we will repeatedly modify these parameters by a small amount in order to reduce the prediction error. Now, in order to reduce the prediction error on every iteration, we must know how to change these parameters. So we must calculate the many derivatives of a cost function with respect to all of these parameters. And if we want any hope of learning the model parameters in reasonable time, we must be able to calculate all these derivatives quickly. One example, the poster example in machine learning, are the deep learning models. In the deep learning models, what you do is that you apply you apply a sequence of parametric functions, vector-to-vector parametric functions, to find the prediction from the inputs, not directly, but by repeatedly applying functions of generally similar shapes, but with different parameters. So we apply a first function to the inputs to find some to find a first intermediate result, first intermediate vector A1. Then we apply another function that generally has the same shape but a different set of parameters to find a second hidden layer, as we call it in machine learning lingo, A2. We apply it to A3 and so on and so forth until we decide that at some point this is the final layer, which we call the output. Okay? So we are going to see in detail exactly why machine learning, deep learning networks are structured in this manner, and what is it that makes them work. But at the moment, I just want you to get that we will be sequentially applying parametric vector-to-vector functions to eventually find a prediction from a set of inputs. And of course, this sequence can itself be seen as the application of one single function, which parameters will be the union of all the parameters of the intermediate functions. And we will train this neural network. To train the neural network means to find reasonable values for all of these parameters, and we will do that on a training set where again we have a number of inputs, and remember that each input is a vector in some dimension n0 with corresponding scalar labels, as we call that in deep learning, which are the true values of y for all of these examples. To train the network means to fit all these parameters theta to minimize the prediction errors on the training set, and then apply the trained model to make predictions on new examples. In this, we will see that the error function is not analytically tractable. It's not even a convex problem. It's not even a convex function of the parameters. And we have no hope of finding a direct expression for the parameters that minimize the prediction error. We must use an iterative algorithm, and we must compute the many derivatives of a cost to all the parameters on every iteration. And to give you a visual clue of how many parameters we have in this in a deep learning model, in this evaluation graph, all the edges, all the blue lines represent a parameter, right? So in machine learning, people often say that they let the data speak. So machine learning models are essentially empty shells that have a lot of parameters and that are fully expressed, fully defined by the parameters alone. And that's why also you have typically a lot of them. Now, an example in finance that maybe superficially can look very similar, it's the calibration of pricing models. In this case, our pricing model is something that will give us an estimation of the value of a product, y hat, as a function of the parameters of a product, for instance, strike, expiry, maybe barrier if we deal with exotics and so forth, and a number of parameters of the model, such as volatility, the initial spot price, maybe the yield curve, and so on and so forth. So here we consider the product, the parameters of a product as the inputs, and the parameters of a model as the parameters, the weights that we want to learn. We have a training set, which in this case we call a calibration set. That's a certain number of financial products, each with known features, X, so known strikes, expiries, barriers, what have you, and for which we know we observed the market price, the true market price Y. And the calibration process consists in fitting these parameters theta to minimize to minimize the pricing errors on this training set, usually the sum of squared pricing errors. And then we can confidently, hopefully, apply the calibrated model to price over products, which values are unknown, right? That's typically how we work with financial models. Again, with a very remarkable exception of Duper's model, where we get the parameters as a direct function, as an explicit function of the observed market prices of European options, with the exception of Bruno's model, we must find the best parameters by iterative optimization. And the go-to algorithm in finance for decades have been Loewenberg-Marquardt. It's a classic algorithm that's explained in a lot of articles and textbooks. Recently, I read this free ebook by Boyd and van der Berg. It's not about finance, it's about applied linear algebra. And I think it's the clearest and most enlightening description of Loewenberg-Marquardt I have seen to date. So if you're interested in how exactly this algorithm works, I definitely recommend this book. It's also explained with code in numerical recipes, as you may know. So again, on each iteration, with Loewenberg-Marquardt or another optimization algorithm, we must compute the cost on each iteration, which means that we must price all the calibration instruments, which may be costly, depending on the model. And we also must provide the algorithm with all the derivatives, dc over d theta of all the derivatives with all the model parameters, so that it knows how to modify these in order to reduce the calibration error. So I have two comments I would like to make on calibration. First is, among practitioners, we always consider calibration as best practice. We wouldn't think of applying a pricing model before we calibrate it to market data. And that's kind of natural to us practitioners, but it's not trivial for everyone, because the natural reflex would not be calibration. The natural reflex would be a statistical estimation of the parameters. And actually, a few months ago in Rio, I made a talk for the occasion of Bruno Dupier's 60th birthday that was recorded and put on YouTube. I'm giving you a link here. If you want to see exactly why, this is where I explained why, for the purpose of risk management, calibration makes more sense than estimation. So it's really mainly a talk about this. The second comment I would like to make is that calibration is only similar to training machine learning models only in appearance. It's actually an entirely different problem, because machine learning are entirely trained on data. They know anything. They don't know anything except that the data they see and the parameters that they fit on the data. They don't contain any more information. Whereas financial models are not at all entirely defined by the set of parameters. Financial models are meant to be meaningful. Financial model, we spend a lot of effort making them arbitrage-free, making sure that the dynamics is meaningful and realistic. We actually estimate historically a certain number of hyperparameters, like typically correlation or sometimes volatility or volatility, depending on the model, so that the dynamics of a model will be both meaningful and arbitrage-free. So our models contain a lot more information than just their parameters. And besides, you know, machine learning models, they, as you know, as you read everywhere in the press, they work extremely well. Well, they work extremely well as long as, after they're trained, we use them on examples that that come from the same distribution as the data they learn from. So essentially, in machine learning, we deal with interpolation problems. In finance, we typically train our models, we calibrate our models on simple products, and we apply them after they're calibrated to more sophisticated, typically exotic financial products. So what we apply the model for definitely comes from a very different distribution than the products that we use to calibrate it. So this is an extrapolation problem, not an interpolation problem. And we know that when we apply a model kind of blindly, only from the data, it should be intuitive, but it works reasonably well depending on the size of your training set for interpolation problem, but it is extremely dangerous for extrapolation problems. That's why financial models, they're really dependent, their quality and the quality of the risk management strategy that you get from the model will be heavily dependent on the information that you put in the model in terms of the dynamics that you assume and the risk, the arbitrage-free dynamics that you assume for your state variables, and not only from the parameters of these dynamics, okay? So that's why there's a lot of enthusiasm with machine learning these days, and I have actually heard people think that, well, in finance, we do pretty much the same thing as in machine learning. We train our models on some data, we use it on other data, and machine learning works so well, why don't we replace financial models by machine learning? And I actually heard serious people seriously say something like this. And this is bollocks. There's no way that it can work. And it's exactly for this reason. So machine learning definitely has a role to play in finance, and I will show you that it does help us resolve problems that we otherwise don't know how to resolve. And actually Blanca, who is in this room, recently published neural network, well, Blanca in France, recently, sorry? Yes. Published an article where they trained a neural network to find the prices of European options in the context of raw volatility models, where we don't have any analytical formula, we don't have any analytical approximations, and without deep learning, the only way that we can accurately price European options in deep learning models would be slow and heavy Monte Carlo simulations. So this is an example, and there are many other examples where deep learning has an important role to play in finance, but not as a replacement for financial models, in combination with financial models to make the whole system a lot stronger. So that was one family of application that's fitting of models. Another family, important family of applications of derivatives is model risk in finance. So again, once we calibrated our model, we can value exotic transactions, trading books, netting sets, and so forth, and we find the value as a function of product features X, so that will be our inputs, and our calibrated model parameters, theta. So these model parameters, they can include today's underlying asset prices, volatilities, correlations, mean reversions, volatility, and so forth, depending on the model. Now, it's good that we have a calibrated model that we can use for pricing, but clearly our work in finance is not about pricing, it's about risk management. So what we're really interested in are the risks, the differentials of this function f with respect to the model parameters theta, because it tells us how we should hedge our portfolio, our transaction or portfolio of transactions. So these model risks, that is the collection of df over d theta, and we have potentially a massive number of parameters. For instance, in Black-Scholes, we just have a few: spot, volatility, perhaps rate and dividend yield. But as we start moving, increasing the complexity of a model, the models that we use in practice, the more realistic ones, they immediately start having a massive number of parameters, like in Dupier's model, which is, as you know, the simplest extension of Black-Scholes, consistent with today's prices of European options. Well, the parameters are bidimensional, theoretically continuous, local volatility surface. And if we squeeze local stochastic volatility in there, in addition, we have the vol of vol, the correlation between spot and vol, and so forth. Perhaps a mean reversion of volatility, and more, depending on your model. For interest rate models, even the simplest ones, your model parameters include a theoretically continuous initial yield curve. So you don't have the notion of what is my initial asset price, where your asset price is not an asset, it's a continuous collection of interest rates of different maturities. And in addition, these days we have spread curves that we must model consistently, and the volatilities of all these guys, which depending on the model may be a curve or a surface. And for multi-factor yield curve models, we also have correlation. We can have mean reversion for the shared families of models, and so on and so forth. And then we have the multi-currency models, the so-called hybrid models, which we also apply in the context of capital calculations and XVA, which are basically combinations of all of the above for all the currencies in my training set, plus in my netting set or my portfolio, plus all the forex rates and all these volatilities, and of course a giant correlation matrix between all of these guys. So routinely we deal with thousands or tens of thousands of model parameters. And the valuation itself, the valuation of an exotic transaction or a trading book, is generally expensive in itself. Typically, we tend to use high-dimensional models these days, for which we can't really apply quick and light finite difference techniques, and we tend to use to apply Monte Carlo simulations, which is universally applicable, but rather expensive, computationally expensive algorithm. One other layer of complexity that I'm not going to cover in this presentation, it's that we're not interested in risk to the model parameters, but risks to the market variables, to risk with respect to something that we can observe and trade on the market, and to which we generally calibrate the model parameters. So for instance, in the context of Bruno's model, we're not really interested in risk with respect to local volatilities, but we want risk with respect to implied volatilities, the things that we observe, the things that we can actually trade to hedge our risks. So there are really two ways you can go about it. Either you can internalize the calibration process in your pricing. So you consider that your pricing function directly goes from market variables to the price of your portfolio and internally contains calibration as a first step. And you differentiate through this. This is not advisable. Typically, it will to try to differentiate by any method through an iterative optimization can lead to very unstable or outright wrong risk sensitivities. The best practice, at least if you can, and I will teach you how, of course, calculate a large number of model risks quickly, is to first calculate all these model risks and then translate them into market risks. But this translation is not something that I will cover today because we won't have time. Jasper, Andreasen, and I worked a lot on this subject together, and I kind of gathered our thoughts and results in a paper that I made available online. So you can look into this paper to see what strategy you can apply once you have your model risks to turn them consistently and safely into market risks. So now in all of these applications and many others, I just gave you a few examples, we have a scalar function f of many inputs or parameters, and this function is typically expensive to calculate. If a function was calculated in a microsecond, it really wouldn't matter. But it's in these examples and in the examples of interest to us, this is not the case. The function is expensive. Typically n takes a large number of inputs. Same thing, if we want only to calculate 3 or 4 differentials, it's really not worth putting the effort to understand and implement AD. But it's when we have thousands of inputs, as in deep learning and in finance, in modern finance, this is where it makes the most major difference. And the goal is to compute the sensitivities of f to all of its inputs. And conventional differentiation, as I explained in the introduction, is of linear complexity. We think of derivatives in terms of finite differences. Derivative is actually mathematically defined as the limit of a finite difference. How does it affect my result if I bump one parameter by a small amount, leaving the other parameters constant? And it helps intuition to approach derivatives in this way, to think of derivatives in this way, but it also seems inevitable that in order to calculate 1,000 derivatives, I must evaluate my function 1,000 times in 1,000 of different scenarios where I bump one parameter by a small amount, leaving all the parameters constant. And it seems inevitable that in order to calculate 1,000 derivatives, I must evaluate my function 1,000 times. And we are going to see that this is not the only way. But conventional differentiation, the differentiation by finite differences, is obviously of linear complexity in the number of inputs or differentials that we want to calculate. Adjoint differentiation, on the other hand, is an algorithm to compute analytically all the differentials of f in a time that's independent of the number of parameters, the number of differentials. With an efficient implementation in practice, it takes around 4 to 10 times one evaluation of f to compute all its differentials. So here I have an example where, for instance, say that you have a function which evaluation takes 1 second, and you want to calculate 1,000 derivatives. With conventional differentiation, it will take you 1,000 function evaluations, 1,000 seconds, that's a bit more than 15 minutes. With AAD, you can calculate all these same derivatives in less than 10 times one function evaluation. That means less than 10 seconds, as opposed to 15 minutes. That's the kind of speed up that you get from this technology. And that's why this is seen so important today. And so this is actually what's why there is a bit of hype surrounding AD today in finance and machine learning, because in finance, we apply AD to compute thousands of complex risks accurately in reasonable time. In machine learning, we apply AD to compute the gradient of the cost functions to many parameters in constant time. So it's really the same technology that powers investment banks to estimate financial risks and deep nets to learn their weights. AD is what allows banks to compute massive amount of regulatory risks in real time, to also powers your telephones so that they can recognize you and your friends on pictures in reasonable time. And it's really the same technology at play here, even though it's been independently derived by different people in different scientific fields, but it's sometimes called different names. In deep learning, it's called backpropagation, but we're going to see that it's really the same technology we're talking about. And AD is largely credited for the recent spectacular successes in the field of deep learning. So, very brief history of AD. It's been invented in the 1960s, so it's not a particularly new technology. It's been called the holy grail of sensitivity computation. It's been classified as one of the 30 greatest numerical algorithms of the 20th century, but it did not take firm hold in the computer science community until the 1980s. It's only after the 1980s that it started to be applied in deep learning to efficiently compute gradients of cost functions. It's in the computer science community, it's known under many names, including backpropagation, or simply backprop, reverse differentiation, backward differentiation, adjoint accumulation, algorithmic differentiation. You can hear all these names or read them in research papers. They all mean the same. This is the same thing we're talking about. In finance, it was not adopted until 2006. There's been an award-winning, a deservedly award-winning paper by Mike Giles from Oxford and Paul Glasserman from Columbia. Article was called Smoking Adjoints, and it was the first article, that established how we can apply this extremely powerful technology in finance, right? And yet, it remained for another 5 to 10 years, it remained a bit confidential. People in finance did not fully understand this technology, did not fully trust it, and kind of thought that it was a nice, interesting theoretical result that was not so likely to work in production. My colleagues of Danske Bank and myself, we believed in this, in the potential of this technology, and we spent a few years on a large-scale implementation in Danske Bank's XVA systems. We combine it with parallel Monte Carlo simulation and so forth, and we kind of provided the market with a proof of concept that this technology does work in production on a large scale, and actually gave us results above our initial expectations. Like, we know the maths, we know that it has to calculate thousands of derivatives in 4 to 10 times one function evaluation, and yet when we see it on a large scale, in a large scale production context on a computer, it's hard to believe. It still looks like magic. I will make you a quick demonstration in 5 minutes. It's really, it really feels like dark magic. So today it's widely adopted in finance for both risk and calibration, but it's amazing that an algorithm that powerful was adopted that late, nearly 50 years after it was invented. So in the preface that he kindly wrote for my book, and that's actually available online in itself, if you don't want to invest in the book, you can still read Life's preface on this link. Life argues that these delays are mainly due to the complexity of implementation, and to some extent, it's true that there are many challenges in the practical implementation of AAD in large-scale production systems. That's why it took us a few years to Jasper, our colleagues of Danske Bank and I, to implement it in Danske Bank's XVA system. We had to resolve a large number of practical implementation problems that are all described in the book. But it is it has been, it's not as easy as finding an implementation of an AAD library somewhere and instrumenting your code. What we are, in the way we are going to see it today, it is pretty much the case, but to do it on a large scale, you really need to intimately understand what's going on and how to apply the right pieces in the right place. Anyhow, so delays in adoption due to complexity, also lack of teaching material. So also what motivated me to publish this book, because for somebody who wants to learn AAD, in the context of finance, there wasn't much out there. And also the fact that AAD is, even though it's an application of rather simple mathematics, mainly the derivatives general, it's kind of mind twisting and generally rather poorly understood. So this is AAD, adjoint differentiation. What about AAD with another A here? AAD is automatic adjoint differentiation. That means an automatic implementation of AAD, whereby developers only produce the evaluation code for the function f, and it's the framework that automatically produces the constant time differentiation code to calculate the derivatives. So developers don't need to write complicated and error-prone AAD code. I will show you some of this. And differentiation code is automatically updated when evaluation code changes, right? It would be a real nightmare if you had to write your differentiation code by hand, because anytime you change anything in your evaluation code, you would need to modify your differentiation code accordingly, right? AAD is automatic. It figures out automatically how to differentiate given evaluation code, which means that if you change your evaluation code, the differentiation code, we will see to what extent it's code or not, will be updated automatically. So one example is of an AAD framework is TensorFlow. That's one of the most popular frameworks in machine learning. It's written in C++, and actually part of it is written in CUDA, so that it can delegate matrix calculations to either multi-core CPU or GPU. Has APIs in Python and many other languages. And what TensorFlow does, it allows client, it gives an API to client code to create evaluation graphs. And once the evaluation graph is created, you can tell TensorFlow to evaluate this evaluation graph and run AD through it to automatically and efficiently compute all the derivatives. So, yeah, well, because AD is generally not sufficiently well understood, and because there's a lot of potential demand for teaching material to understand this technology and how to implement it, we, my colleagues of Danske Bank and I, decided to document our work and publish a book about it. I volunteered to write it because I thought, well, now that the work is done and it works in production, how hard can it be to document it? Well, I figured wrong. It took me months of hard work, day and night and weekends, to actually document our work in a proper form. So even though I volunteered and I ended up writing this book, you have to bear in mind that what it documents is the work of an entire department under the leadership of Jasper Andresen. So what do I have here? This book teaches the modern design and efficient implementation of financial simulation libraries, because that's a kind of a prerequisite to instrument it efficiently with AAD. It also teaches the implementation of parallel simulation libraries, since even our phones are multi-core these days. I mean, we owe it to ourselves to produce multi-threaded code that uses parallel code that uses our hardware, whatever we have, to its full potential. And of course, most of the book is dedicated to AAD, which is covered in deep detail from the mathematical foundation to the practical implementation, the very hard problem of memory management and checkpointing, and so on and so forth. And the book also, we made the decision to package it with complete professional code in C++. For avoidance of doubt, this is not the code that we produced in Danske Bank. This is a simplified version that has been produced purportedly for the publication, but this is professional and especially scalable to production C++ code that comes with the book, and that's freely available on the GitHub repo if you want to have a look at it. You don't have to invest in the book to access the code. So because I couldn't help myself, I want to show you a few reviews from early readers of the book, especially my personal favorite is Vladimir Peter Barks, who compares our work to Robert Mertens. So I'm not sure what Vladimir had to drink, but for sure this one is never getting old. So what we are going to do in these 2 days, first I'm going to demonstrate AAD to you, because I thought before I explain the magic trick, maybe I can just show you, I can show it to you. Then we are going to see how agent differentiation and backpropagation work in the context of deep learning. And then most probably tomorrow, we are going to generalize this, and I'm going to show you how the same backpropagation algorithm applies not only in deep learning, but in the context of any arbitrary calculation that's programmed on a computer. So from the value of a portfolio of exotics to the calculation of capital requirements for an investment bank, any calculation that you implement on a computer can be backpropagated, same as a deep neural network. So I'm going to see how this all generalizes and connects together. And finally, I will show you how to implement all of this in very simple C++ code. We are going to we are going together to achieve, I think you will agree with me, pretty spectacular results with extremely simple C++ code. We are not going to achieve the same speed as a fully optimized C++ code like the one that comes from the book, but with beginner level C++, once we understand how AAD works and how it's implemented, we are going to see some results that only 15 years ago would have been thought of as unimaginable. So as a demonstration, I will not demonstrate an XVA because that would be very heavy, but I'm going to demonstrate an implementation of Bruno's model of 1992. As you know, it's an extended Black-Scholes dynamics. In the absence of rate, dividends, etc., the volatility is not a constant, but a deterministic function of a current spot and time. This model is calibrated with Bruno's celebrated formula, which there's a square missing here, actually. The local variance is 2 calendar spreads over a tight butterfly. And in this case, we're not interested in calibration, so we just we assume that we have a local vol matrix, that local vol surface that has already been calibrated to the market. and that is given to us as a bilinearly interpolated local volatility matrix. And with this model, oh yes, the volatility matrix that we will be using is a matrix of 21 spots times 36 times. So all in all, we have about 1,000 local volatilities and one initial spot, so a total of 1081 model parameters. And we are going to use it in a somewhat unrealistic context, but that's works for our demonstration. We are going to price a 3-year weekly monitored barrier option of strike 120, barrier 150. So as you know, I think this is a European call option that dies if the barrier is breached, if a spot fixes above the barrier at any one of the monitoring times before expiry. Now, this problem of a barrier in Duper's model can be solved either with Monte Carlo or finite differences, because in this case, this is a rather simple problem of barrier option in one-factor dynamics. However, the application of finite differences is really restricted to low-dimensional models, and what's really of interest to us is how all this works in the context of Monte Carlos, which are computationally more expensive and converge a lot slower. So we will focus on Monte Carlo simulations here, and we are going to run this model with 500,000 paths and weekly time steps over 3 years. That means 156 time steps. The implementation is in C++, exported to Excel. So for those of you who don't know how to export your own C++ code to Excel, I recommend you learn about it because it's extremely convenient to be able to use Excel as a front end for your own C++, for your own implementations in C++. And actually on the GitHub repo, there's a folder Excel CPP where you will find a tutorial that I wrote for my students that should get you up and running with exporting C++ to Excel in a couple of hours. So we applied the generic library design with efficient implementation. I mean, this is code that has been optimized to the extreme. It's parallel implementation. It uses Sobol, quasi-random numbers, as is best practice in finance. If you want to learn about it, I wrote about it in chapters 5 and 6, and I made the part of Sobol freely available online. And it applies an advanced implementation of AAD for maximum speed with so-called expression templates. The hardware is my quad-core laptop, and I'm going to show you the performance. Yeah, so as I said, we have here a pre-calculated, pre-calibrated local volatility matrix of 1,000-something local volatilities. These are the ones that we are going to use in our Duper model to price the barrier. Strike 120, maturity 3 years, barrier of 150. Don't worry about smoothing net yet. We will cover that later. We will monitor the barrier every week, and we will have a simulation step every week. We will use Sobol numbers with 500,000 paths, and we are going to simulate them in parallel. So here I'm just pricing both the barrier and the European option in this model with Monte Carlo, and I get a price in less than 1 second, 0.8 seconds. Okay. Now, the real goal here is to get all the sensitivities, all the Vega buckets, the micro buckets, as Bruno called them, the sensitivities of this barrier price to each one of these local volatilities. And these ones we get in pretty much a few seconds. Now, this is what you see is a pretty display here. But these are all the derivatives of a barrier with respect to every cell in the local volatility matrix. On the chart, I just showed you a few sensitivity curves of a barrier option price against local volatilities function of a spot for a few different times. So this, for instance, this green line is for time 275. So this is the last time in the local volatility matrix before the maturity of a barrier. This is why we have so many swings. And as expected, perhaps we are long local volatility around the strike and short local volatility around the barrier. And you can see that this is pretty smooth, not perfectly smooth, but pretty smooth, pretty nice risk report that we get there, something that we usually don't get with Monte Carlo. Usually it's with finite differences that we get this kind of smoothness. But you also can see that it's not perfect. It's not perfect because I have a bump here on the red line that really shouldn't be there. But if I can calculate derivatives with this kind of speed, then why limit ourselves to 500,000 paths? Now, this 500,000 paths, we get the 1,000-something derivatives. We get them in just less than 1.5 seconds on a laptop. Okay, but I may as well do it with 2,500,000 paths to get an even smoother surface. And I think this kind of artifact bump should disappear, or at least it's much, much better. After 5-10 million paths, it actually completely disappears. So that's also the point about AAD, because it's good that it allows us to do faster things that otherwise would take minutes or hours, but it also allows us to do things that we otherwise couldn't do at all. I mean, it would be unthinkable without AAD to calculate 1,000 Vega buckets over 5 million paths. But with AAD, with this implementation, it's not a problem. And I promise to you, I'm showing you the real thing. I'm not connecting to Danske Bank's farm or anything. I'm really calculating all this in real time on my slim laptop. So 5 million paths now. And unless I'm cursed, in a few seconds, we should see the risk. And now you can see on the red line, we have no more bumps. Okay? So what I'm arguing in the book is that 20 years ago, we were mainly working with finite difference methods. Finite difference method is the fastest, the most efficient method known to finance. With finite differences, we can calculate a price in a microsecond. We can calculate a 1,000 of differentials in a millisecond. It's, sorry, rewind. A price in a millisecond, 1,000 differentials in a second. That's what finite differences give you. What I am arguing in the book is that we can't, we have achieved a level of complexity and sophistications in finance over the past 20 years, where we no longer apply simple or low-dimensional models where finite differences are applicable. So we have to, in almost every context of practical relevance in modern finance, we have to apply Monte Carlo simulations. And Monte Carlo simulations are slow to converge, they are computationally demanding, and it's with the addition of parallelism and technologies like AAD that we manage to achieve a similar level of speed and accuracy that was only possible with FDM in the context of Monte Carlo simulations.